Hello everyone, welcome to this quick and clear walkthrough of an acid and base titration problem involving a weak base and a strong acid. My name is Tengku Amira Zahia.
And my name is Afif Lukman bin Bahrain.
And my name is Muhammad Danish Irfan.
By the end of this video, we'll be able to calculate pH at each stage of a weak, base, and strong acid titration. Use key concepts such as base dissociation, buffer equation, and acid hydrolysis. Draw and understand the titration curve. And finally, select a suitable indicator based on the equivalence point.
Here's the questions we're going to solve. First, calculate the pH at each point listed for the titrations of 100 ml of 0.1 m cocaine, with the Kb equals to 2.6 multiplied by 10 negative of 6, with 0.2 m HNO3. The points of calculate area is 0.0 until 60 milliliters. And the second one is we need to draw the graph of pH versus Va. We've given the titrations between a weak base and a strong acid. Specifically, we have 100 millimeters of 0.1 molar cocaine. And yes, cocaine in this context refers to a chemical base. And it is being titrated with 0.2 molar nitric acid, which is strong acid that fully dissociates in the water. We've also told that the base dissociation constant, or Kb, for cocaine is 2.6 times 10 to the negative of 6. That means it's a weak base, not fully ionized. And we'll need this value later to calculate the pH through the hydrolysis and the buffer equation. The questions also give us 12 volumes of nitric acid added, from 0 up to 60 milliliters. These represent key stages, which is before any acid is added, during the buffer region, at the equivalence points, and after excess acid is added. Lastly, we were asked to draw a titration curve, a graph that shows how pH change as we add the acids. And the x-axis will be the volume of acid added, and the y-axis is the pH. Let's begin with what happened before we add any acid at Va equals to 0.0 ml. Our solutions contain only cocaine, which is a weak base. This is because it is partially ionized in water, and it produces hydroxide ions and result in a basic pH. So, the pH at the very beginning is about 10.71, indicating a weakly based solution. Now, as we slowly add HNO3, a strong base acid, it reacts with a weak base to form its conjugate acid. These create a buffer systems. In the buffer, we use the Henderson-Hasselbalch equations to calculate the pH, where the B is uncreated base and BH plus is its conjugate acid. Now, let's calculate the pH after adding 10.0 ml HNO3. Now, when the volume is 10.0 ml, the moles of acid added is 0.002 mole, and the remaining base is 0.008 mole. Hence, the total volume is 0.1100 liter. In order to get the pH, we use the Henderson-Hasselbalch equations, and the pH obtained is 9.02. We use the same method of calculation for 20 ml also, with the obtained of pH value equals to 8.59. Now at 25 ml, we are halfway to the equivalence point. The amount of acids and remaining base is exactly the same, and we obtain the pH value of 8.41. The same method of calculation is applied at the volume of 30 ml, 40 ml, 49 ml, and 49.9 ml in order to obtain the pH value.
Now we have reached a critical stage in titration, the equivalence point, which occurs at 50.0 milliliters of nitric acid added. At this point, we have added exactly enough acid to neutralize all of the cocaine base. That means all the base have reacted to form its conjugate acid, BH+. Since BH+ is a weak acid, it partially dissociates in water to release hydronium ions, H3O+. So now, the solution behaves like a weak acid solution. We already calculated that the acid dissociation constant for Ka for BH+ is 3.85 times 10 to the negative 9. At this point, its concentration is about 0.0667 molar. H plus equal 3.85 times 10 to the negative 9 times 0.0667 equals 1.60 times 10 to the negative 5. pH equal negative log of 1.60 times 10 to the negative 5 equal 4.80. Notice the steep drop in the titration curve right at this point, which marks the sharp change in the pH when the weak base is completely converted to its conjugate acid. We are now transitioning into the acidic region of the titration. Let's see what happens when we keep adding more acid after this point.
Now that we've passed the equivalence point, meaning we've added more than 50 milliliters of nitric acid, there is no more cocaine base left to neutralize it. From this point on, the solution contains excess strong acid, and this excess directly determines the pH. The hydrogen ion concentration, or H+, is 0.00002 divided by 0.1501, which gives 0.001332. That gives a pH of 3.88. Hydrogen ion is 0.001 divided by 0.1510, which equals 0.0066. Negative log of 0.0066 gives a pH of 2.88. Hydrogen ion is 0.002 divided by 0.16, which gives 0.0125. Negative log of 0.0125 gives a pH of 1.90. As you can see from the curve, the pH drops sharply right after the equivalence point, then gradually levels off as more acid is added. This plateau reflects the increasing dominance of excess nitric acid in the solution. Finally, we'll wrap things up by choosing the best indicator for this titration based on the curve we've just completed.
Now that we have completed the titration curve, let's talk about choosing a suitable indicator. As we saw, the steepest changes in pH occur right around pH 4.8, which is the equivalence point. That makes methyl red a great choice of indicator since it changes color between pH 4.2 and 6.3. This means it will give a clear, visible color change right when the titration reaches its endpoint, minimizing error and improving accuracy.